everyone. Welcome to our webinar towards an Australian ecosystem foundation model. It's great to have so many of you here with us today online from all sorts of countries around the world. And I've got the slide up so you know that you're in the right webinar. But now I'm just going to move the slide so that I can get an acknowledgement of country. So want to say that we pay our respects to the traditional custodians throughout Australia, the elders past and present and emerging, and anyone that's joining us today, and acknowledge the important role that Aboriginal and Torres Strait Island people continue to play within our community. And today I'm joining you from the land of the Juggera and Turrbal. So again, thank you very much for joining us today. And for those who haven't met me yet, I'm Beryl Morris, and I'm the director of TERN, which is Australia's Ecosystem Observatory. And just a couple of words about what TERN is. It's a national research infrastructure project. It's funded by the Australian government, and we've been around since 2009. In fact, this year, it's our 15th anniversary of the first data that we produced. We make observations and we collect and aggregate data that's multi-scale. And what we mean by that is that it comes at continental scale, regional scale, and local scale. We also collect physical samples, and we make up a lot of data tools, apps, protocols, and so on to make it easy for you to use that data. And our field sites where we collect the data are available to you if you want to use them for your research. Our data covers terrestrial and coastal ecosystems, and we define infrastructure, research infrastructure, is the people and the instruments and the data. So it's quite a few things. So our talk today has got 4 people in it, and 2 of them are going to fill one of the time slots. We're going to start off with Dr. Siddheswara Guru, who is from TERN, and you can read all about Guru in the bios that we've given you. But I just want to highlight that he plays a really key role in making Australia's ecological data more accessible and interoperable and useful for research and policy and everything else. So he's passionate about enabling better decision making through open data and innovative digital tools. So you'll be hearing from Guru first. And then we're going to be followed up by Dr. Andrew Prater and Dr. Ruzbeh Balagi, both from CSIRO. So Andrew is a bit of an atmosphere specialist, and his current research interests are in atmospheric correction with remote sensing, developing methods for producing cloud-free satellite imagery with high spatial and temporal resolution to use in geospatial foundation models. So that's good news. And Ruzbeh is also from CSIRO, and he's actively involved in the development of open source software and machine learning models and leveraging high performance and cloud computing to optimize ecological workflows and large spatial predictions, all really useful for the topic that you're going to be talking about. And our anchoring at the end is Dr. Stefan Hajkovic, who's Chief Research Consultant in CSIRO. And Stefan works at the interface between science and technology and policy and strategy. He actually is responsible for a global megatrends bestseller book that CSIRO publishes. And over the past year, Stefan's been working on digital technology and AI strategy policy projects for government and industry. And he also wrote Australia's National Artificial Intelligence Roadmap and Ethics Framework. And he's currently involved in leading a portfolio of research and consulting work on AI. So as you listen to the talks, we won't take questions during the talk or until the end of the whole session. So if you have questions, you'll find that there's a Q&A button on your screen. So you can just pop your question in there. Some of them might get answered as we go if they're very specialist. If you have technical problems, put those in the chat session. But otherwise, use the chat session to tell us where you're from and pass any other comments, but put the questions in the Q&A. So I'm going to hand over to Guru to lead us off. So I will stop sharing and I'll turn off my video.
So good afternoon. I'm Siddhesh Guru and the program lead for the TERN Data Services and Integral Platform. Today I will talk about a brief overview of a foundation model and then how that can be used to enhance the ecosystem science research. So the foundation models are basically general purpose AI models trained on the vast amount of data to fulfill the range of general tasks. It was first coined in 2021 by in Stanford, um, just to provide a bit of a clarity on the different, the modeling paradigm in AI. So if you look at the what we mean by the foundation model is that obviously this picture is more around the multimodal. What it means that it takes like a different variety of data sets, and then trained to create a model. And then that model is used to adapt to your multiple downstream applications. So of course you fine tune that and then use that as a multiple applications. So one of the thing is that you don't have to create everything from scratch. You create like a general purpose model, the big model, and then you fine tune to create to tailor for the multiple applications. So I think I'm pretty sure people are aware of the traditional AI. Typically, in a normal machine learning algorithms, you have like a trained data set, and then you model using that data set, and then you build that model for a particular task, and then you run that model. So a fair bit of like image classification recommender works like this. Whereas in the foundation model, you have like a wide variety of data set, and then it learns based on that, and then it performs various tasks. So if you step back and then think about the foundation model is predominantly more on the neural network side of the things. Just imagine how human being learns. So if you take any human being, so we do learn based on somebody instruct us when we are young. Our parents teach us something. And after that, we learn from the environment, friends, relatives, and then a lot of things we observe and learn as well. And then the learning evolves as well, depending on the environment and everything. So that is exactly what the foundations model is. So that's why it's called self-supervision learning. So basically, it iterates and then learns, and then take a feedback and then keep learning it as well. Uh, uh, so some of the characteristics, the main thing is that it is a self-supervision. Learning is based on that one, and then basically it requires a massive amount of data set to build that knowledge. So the training requires a substantial amount of data. And then any subsequent application is basically the fine tuning to adapt to your multiple application. So what I showed is that the multimodal, so basically takes a multiple variety of data set, can be used to train it. And then you might have heard that, so for example, ChatGPT has got like a 300 billion parameters, that kind of a thing. So basically the number of parameters used for the training is quite large. What it means that the weightage in the neural network between the input, the features, and the weightage that is added will be like a massive amount of number. That means that, it's easy to predict the multiple permutation combination. So just briefly provide the very popular other terms in this domain. So one is the generative AI. I think this kick-started the foundation model paradigm, everything. So with any traditional AI, so it used to predict certain things, whereas the generative AI, it can generate a new contents. It's just like text, code, image. You can write a poem, abstract, thesis, everything. Whatever you can do is the in ChatGPT. So basically, with the massive number of things, it with the untrained data set, it train itself, learn the pattern and relationship between the data. That's why you have so many parameters, and then it will predict the future things. And then you might have heard about talking about the large language model. This is basically the AI system that works with the language. So basically, it can understand and generate a human-like text. And a classic example is what ChatGPT and Gemini does. That is a large language model. So if you look at overarching things, Gen AI is the field, and then you can say that the foundation model, and then large language model is one type of foundation model as well. So the large language model is a very specific form of the foundation model. So there are a fair bit of challenges in developing this foundation model. So the first thing is the data bias. So if you don't have a good representative data, whatever in the training data set, whatever the output will also be a quite biased thing. Especially in the large language models, the fair bit of a data set, everything, whatever is in the internet is used. So you never know, there may be a sensitive information that is used to train the model. And then that is a bit of an issue. And then even the adaptation is not a trivial task, because you need like a really good training data, as well as you should be really good in understanding the model as well. The trust is another issue where you need to understand how the model works, how it infers, just to develop a bit of a trust in the model. You don't want to use that as a complete black box without knowing how it works and why it derives that information. So one of the major thing is the cost, because it takes so much of data, and by default, all the algorithms are parallel algorithms. It runs on the GPU. The running cost is quite high as well, and as well as the human cost, the people who have expertise is also quite high. You might have heard a couple of days back how much money Facebook was willing to pay for the key people who knows what they are doing. And one of the common thing is here is the hallucination. So basically, it provides a bit of you have a certain data set, and then the foundation model got is completely wrong. It tried to provide something wrong, which the human won't contextualize. So again, this can be fine tuned, and then make sure that it doesn't provide a wrong information. So the basic thing is that people should know what they are doing when they are developing this model to make it more productive. Okay, so how they are relevant? So we come back to the relevance in our ecosystem science. If you look at the ecosystem science, so we collect data in the vast, varied, and format, and then it's growing fast. So the data are of a different scale, from a continental scale to the in-situ sensors to the point data, collect using a wide variety of methods, including satellite remote sensing, aerial vehicles, and then the in-situ sensors, like a multiple varieties of sensors, human observations, as well as the expert elicitation as well. So which is one of the things which we don't use it as part of the structured data. So that is a very critical component as well. So there's a case for the foundation model to process all this data set because of the diversity. And then the good thing about this is, you develop this based on the data set derived from Australia. So this is what we are proposing, where you bring your data and then they build a in-situ sensor foundation model, the observation data, and then the geospatial AI foundation model. So that is the infrastructure, and then you work with them to fine tune that to have a subsequent applications. So in this way, what happens is that you build one infrastructure to process all the trained the model with all the data set available, collaborate with the multiple partners to process them, and then work with the collaborators and then to develop the application on top of that one. So in summary, so we can consider the foundations model as a research infrastructure. because it provides a base, a general purpose base of a model. And then there's a case for definitely an Australia-centric foundation model trained using the Australian data sets. So now I will hand over to Andrew to talk more about the geospatial foundation model. Thank you.
Share my screen. Okay, hope everyone can see that. Right, so thank you for the introduction, Beryl. I'm Andrew Prada and this is Rizbe Valabi. We're from CSIRO. And today we're going to talk about geospatial AI for Australia. In the first half of the presentation, I'm going to talk about some of the challenges we have, long-standing problems we have in remote sensing. And then Rizbe in the second half is going to talk about how geospatial foundation models may be the solution that we're looking for. So Australia requires accurate and timely environmental monitoring to understand ecosystem change, but also mitigate significant natural hazards. Some of the natural hazards that will be in recent memory for lots of people are the Black Summer bushfires in 2020, which happened on such a large scale that it was very challenging to quantify and analyze the bushfire extents during this natural hazard. And then the next year we had record flooding in New South Wales. And again, this was a natural hazard that occurred in Australia that was on a significant spatial scale. But we also want to be able to monitor the impact of these natural hazards on our environment. And so this is where TERN plays a key role in environmental monitoring. This image here shows some fieldwork that I was involved in, where we went to South Tasmania to look at the impact or the regeneration of vegetation after a bushfire event. But as I've already alluded to, the common problem with these applications is they occur on large spatial scales. And so satellite remote sensing or Earth observations provide continental scale monitoring to map these hazards in a timely manner. And so here is the EO perspective on these different natural hazards and also in the environmental monitoring case. So we have an image from MODIS showing the massive bushfires occurring across two states, Victoria and New South Wales. And then we also have a higher resolution Landsat image showing the extent of the flooding at the Hawkesbury River just northwest of Sydney. And then another satellite image on the right-hand side here that a lot of people might not be used to seeing. It's actually a cloud-free image over Tasmania, where it demonstrates the extent of the forests in Tasmania that we would like to be able to monitor. But as many people who've worked in remote sensing or Earth observations know, this data is not just pretty pictures or just of imagery. There's a lot of work that goes into correcting this imagery so that it can be useful in downstream applications. This image here is a Landsat image over the Lucinda Jetty, which is a calibration validation site run by the CSIRO. And what you can see here is the blue hue of the atmosphere in the intervening between the top of atmosphere and the surface. And on the right here is what happens when we do an atmospheric correction, which is essentially accounting for the scattering in the atmosphere of the solar radiation that we measure from satellite. And we have developed over time a system to produce atmospherically corrected, normalized satellite remote sensing data for a given sensor so that we can account for these variables in the atmosphere. But we also want to be able to combine different types of satellite observations. And this is something that we call spectral harmonization, which essentially is a method that accounts for the fact that a given satellite sensor instrument will have a different type of measurement. So for example, Landsat, the Landsat green will look different to the Sentinel-2 green. And we need to have a way to be able to harmonize these datasets if we want to use them together. Then, of course, there's the cloud problem. So here's an example of a Landsat scene over southeast Tasmania that is analysis ready. It's had the atmospheric corrections and normalizations that I mentioned before to it. But if you put this in the hands of a user, how are they going to extract insights from it? There's obviously too much cloud in the scene. So one method that we commonly use is to combine multiple observations, which I already alluded to in terms of combining Landsat and Sentinel-2 over some time period. In this case, here's what occurs when we collect multiple scenes over the course of a month, and we can produce a cloud-free image. Now, this cloud-free image, there is a catch here. It's over a month, and it's also not completely cloud-free. If you look carefully, there are pixels that are completely still masked, even by collecting the data over a month. Now, to solve this problem raises another issue, which we call the trade-off problem. So for example, if we want to get to a higher temporal resolution, we can use geostationary satellite imagery. So this is from the Himawari geostationary satellite, where we have observations every 10 minutes at the expense of a coarse spatial scale, so 1 kilometer pixels here. Now, this sort of solves the problem, right? Because we do have the clear sky observations here, but that's on one particular day. If I selected a different day for Himawari, cloud is persistent throughout the entire day. So we're always going to have cloud as an issue. And so this does raise two key problems. One, how do we solve the trade-off problem with multiple resolutions of satellites? And two, how do we deal with pixels that have cloud over them? And how do we predict what surface reflectance might have occurred if the cloud wasn't there? Then we're also having to deal with a huge amount of satellite imagery. I mentioned optical remote sensing imagery earlier, but we also have hyperspectral data where there's SAR imagery, cloud penetrating radar, and also aircraft and drone observations. We want to be able to take advantage of all of these different types of satellite observations. And then there's also this exponential increase in Earth observation satellites with time. So here I'm just showing the cumulative number of operational Earth observation satellites over time. So this also raises the question of how do we choose the right satellite observations for the analysis, and how do we combine them? And now I'm going to pass to Rusbeh to talk about why GFMs might be the solution to this problem.
Thanks, Andrew. Hi, everyone. I'm Rusbeh Valavi. Today, after this, I'm going to provide a high-level introduction to geospatial foundation models, or GFMs. As Guru mentioned and explained what the foundation model in language means and what they are, geospatial foundation models are also large AI models trained on unlabeled satellite imagery and to learn a general purpose Earth representation. Then they can be fine-tuned for various tasks that we use for different geospatial analysis. They use they use multiple data sources and can be adapted to a variety of applications. Unlike traditional models that rely on handcrafted features or task-specific model or architectures, GFMs learn directly from raw satellite data and adapt efficiently to new geospatial tasks. In using GFMs, there are generally two main steps. First is the pre-training the foundation model on a massive volume of geospatial data, like satellite imagery, environmental data, and climate data. This is typically done by large organizations that create a foundation model, like Alpha Earth from Google or Prithvi from IBM and NASA. Second is the fine-tuning step. That is for fine-tuning for specific tasks, like a crop classification or biomass estimation. And this is typically done by user. That being said, the fine-tuning is not the only way to use these models. Another approach is using them for tasks like similarity search, which I'll explain in a few slides. But what how they work, the GFMs. Like ChatGPT that uses a foundation model for language, now we are seeing these similar models applied to geospatial data. They are mostly based on the deep learning transformer architecture, originally designed for text, but adopted to handle image and spatial data, as Guru mentioned in previous presentation. What makes them powerful is their attention mechanism, which helps them to figure out what part of the massive data set that they are using is important and focus on the important spatial, spectral, and temporal features in the image. They are trained on a huge volume of data from satellite, optical images, LiDAR, radar, elevation data, weather data, and even text. But here is a catch. There is no need for label data for generating a GFM. The model trained themselves by learning to predict or reconstruct a part of the input image, which is called self-supervised learning. This was also mentioned in the previous presentation. This way, they can learn a lot of general pattern features from the input data, and then user can leverage these capabilities to predict accurately for a specific analysis. Once trained, these models can be used for many things: identifying floods, land cover mapping, biodiversity modeling, species distribution mapping, detecting wildfires, similarity searching using their embeddings, and more. They adapt to new problems with little extra data, and you can use them for different things. I think it's hard to talk about the GFMs without mentioning the new GFM released by Google. So this is one example of the Geospatial Foundation model that Google newly released as Alpha Earth just a few days ago. As a part of this release, they provided 64 embeddings that represent the Earth. These are 10-meter resolution bands that combine from multiple sources. As I mentioned before, the optical, radar, LiDAR, elevation, climate, and even descriptive text. Similar to how word embeddings capture semantic meaning in language models, so that words like queen and crown appear close together in a language model embedding space, geospatial embeddings aim to represent Earth geography, such as regions that are spatially or functionally similar, also map to nearby points in the spatial embedding space. One can run similarity search on these embeddings to identify functionality similar places on Earth. One example being, for example, you can use this Google Earth Engine app built on Alpha Earth embeddings to find similar areas. Here I clicked on Launceston in Tasmania. This highlights the area with similar city landscape that you can see it clearly. Hobart and Melbourne are highlighted in the embedding space. Another example is a tool created on AWS. You can find forest clearing areas by selecting a known cleared area. Clear benefits of GFMs are adaptability to new problems with little effort, robustness, scalability, performance, and generalizability. So the models that are based on a large volume of data and with a lot of effort, they can generalize very well beyond the small training data that you use for fine-tuning. And at the end, I want to finish my slide by introducing the Geospatial AI for Australia. We are aiming to develop an Australian foundation model, Geospatial foundation model, built specifically using Australian geospatial datasets. This will be a multimodal model designed to capture the diversity of Australian landscape by integrating data from sources like Landsat, Sentinel-1 C-band SAR, Sentinel-2 environmental grids, and even high temporal resolution geostationary satellite imagery. The result will be nationally scaled, adaptable AI framework with the potential to transfer geospatial analysis for a wide range of applications. Australia has been underrepresented in has often been unrepresented in global models. So building our own national GeoAI system is key to unlocking the full potential of Australian research industry and innovation. Now I would pass the presentation to Stefan. Next presentation. Stop sharing. Yeah.
Thank you very much. And I have just shared my screen. Oops. Can I just check if my screen is visible?
All good.
All good. Okay, fantastic. Right. So I'm Stefan Hajkovic. I work in CSIRO, predominantly in the space of strategy and policy relating to digital technology and mostly artificial intelligence. I wrote the National Roadmap for AI in 2019 and also the ethics framework, which is now a set of principles on the ethical use of AI. But in recent times, Professor Eleanor Huntington, who's Deputy CEO of CSIRO, and myself, have been exploring the issue of foundation models. We picked up the work in around 2023 as foundation models were taking shape to understand what was happening across the globe and the implications these would have for the Australian economy. My interests are, I'm actually interested in geospatial foundation models, but all types of foundation model development. And as we've heard from the previous speaker, the vast majority of these foundation models are being built outside of Australia, and we're a downstream user of those models. But I think things are starting to change in both private and public sector. We are seeing some really significant foundation model development initiatives happen in Australia, and I think it's going to grow. So as we look at research infrastructure, and this is what Eleanor's view of the why we wanted to pick it up was, Eleanor really had the idea that AI foundation models would become a new class of research infrastructure. So we're familiar with the massive investments in research infrastructure we've made historically, like the synchrotron, the square kilometre array, the CSIRO investigator, which you're not allowed to call a boat, ship, or even vessel. I'm not sure, but every time you call it a boat, they tell you not to. And then our Pawsey supercomputing centre. So these are really expensive, hugely significant bits of research infrastructure. They provide a foundation for knowledge, discovery, and science in lots of different fields. They're under heavy use, and they're significant sort of foundational infrastructure for knowledge discovery. But we're entering into a new era where we will actually turn to foundation models for knowledge discovery. And they could be geospatial, they could be a wide range of different foundation models, which are trained on typically vast swathe of data, often using unsupervised machine learning at scale. And they're generalizable, used for wide-ranging downstream tasks. Many are LLMs, but anything can be tokenizable. So that was why we proposed this. We wrote the report, Artificial Intelligence Foundation Models, and that's what we think will sort of take shape in the landscape of research infrastructure that supports all forms of knowledge discovery in Australia. A lot of this became possible due to the 2017 breakthrough in the field of machine learning, the generative pre-trained transformer, a hugely important scientific discovery that improved the efficiency of machine learning used to develop these foundation models. And from this, we have the main commercial models that we're all aware of, where billions and billions of dollars are going into the development of these models, and they've become front and center to the investment of the world's largest tech corporations. Some are open access, some are commercial and proprietary. They're multimodal, and then we've also had the case of the Google Geospatial AI model, and I think there's some others under development as well. So we're going to likely see the diversification of different types of models. The tech sector globally is in the phase of restructuring around AI foundation models. You can see as the AI foundation models were released over time, the red bars show us layoffs in the tech sector. It's worth pointing out there is a blue bar next to these, which is recruitment and growth, because companies were appointing as well. But I think the reality is massive downsizing and restructuring here as the AI foundation model hit the global tech corporations, as they were able to use them to do things more efficiently, like write code. But their investment was massively redirected towards trying to win in the space of AI foundation models. And in the public sector too, we've been working with the South Korean company Naver, which is the South Korean equivalent of Google. They actually own 60% of the search market in South Korea, and they've developed a portfolio of AI foundation models. But we were stunned to see this announcement from one of our colleagues at Naver is in a central position here. But they'll be investing 1.132 trillion Australian dollars in the coming years on AI model development, but a lot into developing a portfolio of AI foundation models with a pretty clear objective, becoming the third provider of AI models after US and China, to partly around sovereign capability concerns and risk mitigation as well. But they're effectively betting their whole economy of South Korea on AI models. So it's a really interesting set of things that are going on. The UK Competition and Markets Authority studied foundation models and did a big exercise to sort of document how many there were. They found 120 AIFMs were released between 2023 and 2024, and found overall number of known globally ones in the year 2024, they put it at over 330. I'd say it's a lot larger than that now. In terms of large language models, we probably have over 100 or so high-performing large language models. I'm not I'll show you some research on geospatial AI foundation models. I'm not sure how many actual models there are, but the activity has grown. And I think it will, this global supply of, like I call them brains, effectively, these brains that are being built across the globe to do different things, is going to grow. And there are interesting questions strategically for governments and corporations about whether they build their own AI foundation model, whether they leverage other ones, whether they're fine-tuning an open access model, or whether they're using model distillation and reinforcement learning is also showing to be quite effective. But there's a lot of ways that you can now build an AI foundation model. So, oops. Yeah, but ultimately you need skilled workers, you need data sets, you need compute power and a lot of it, and you need guardrails for the deployment of that model. And it's worth pointing out too that what DeepSeek R1 did was announced in January, where that model got to third top best performing on a lot of benchmarks globally, and really shook the AI world because they did it via reinforcement learning and model distillation techniques off the back of other models. So we can actually, it's shown the effectiveness of those sorts of lower cost techniques. They reportedly did it on only $6 million of GPU time, which is a tiny amount compared to the GPU time put into those larger models. We're also seeing some interesting developments around self-learning. Sakana AI in Japan is something doing this with if we look at the analogy of what happened with AlphaGo 0, when AlphaGo was developed, it was trained on human play data. AlphaGo 0, which was trained on zero human data and played games of Go itself, became a way better player of the game Go. And that was in 2018, I think, that it beat Lee Sedol, the best human player in the world, and will now always win. The question is also whether there is a future where these models are able to use synthetic data or adjust their weights as they're used and improve themselves, and to start to develop beyond the use of human data in them. And that's an interesting question for future development. Interesting developments like weather forecasting. In January this year, we saw a publication in Nature by Google DeepMind researchers where they found their AI foundation model for weather forecasting was better on 97.2% of 1,320 weather targets compared to the best forecasting systems globally. So basically up to the 15-day forecasts, it looks like that AI foundation model capability will now be a better forecaster than pretty much everything else out there. So that shows the possibilities here and the impacts that are on their way as foundation models continue to do things. And I think it's also worth noting that foundation models are also happening in robotics in exactly the same way. The CSIRO team at Pullenvale, who I work with, are very much working on the problem of generalized human language tasks that can be given to a robot so that it can perform those tasks. But the high level, big case studies are Google Gemini for the physical, where the robot can be told to pick up a coffee cup and put it in the dishwasher. and it is able to take those generalized tasks and perform actions. NVIDIA have also developed similar robotic capabilities, but anything can be tokenized in a foundation model, including all the actions of robotics and how a robot learns and interacts with the world. So it's not just limited to the information world. Geospatial is an interesting place to look at, and I think Google's release of its geospatial foundation model is really significant. It's a very powerful set of tools. We're going to see more emerge, and it's great to see this happening out of Australia as well from TERN. But what we can see, this lit review that was published in 2025 by researchers at the University of Texas in Austin and published in the International Journal of Applied Earth Observation and Geoinformation, shows us the big growth in the literature in recent years. The last 10 years, you can see it's really the number of publications about geospatial AI has risen pretty steeply. I don't have the data set here, but it also shows the bulk of them are coming from United States. China is doing a lot in this space as well, based on publishing. How many geospatial foundation models are out there? How many high-performing ones? I don't know. If we look at large language models, where there's a lot more things like the Artificial Intelligence Index, which show us the spread of capabilities. I'd say there's up to about 100 high-performing LLMs or multimodal models. Some of them involve video and audio as well out in the world. And this is one ranking, which has at the current time Grok at the top, with O3 Pro, Gemini slightly after on a range of tests, including Humanities Last Exam. I think Grok actually just recently topped the Humanities Last Exam with about 21% of the 2,700 questions correct. But this list is changing and reshaping continuously, and there's obviously huge amounts of investment going into it. Training compute, the petaflops consumed by the development of these models shows a pretty strong linear upward increase. Could well be that electricity becomes a key limiting factor in the development of new foundation models as we go into the future. This was something that was studied by Epoch AI, which is a large research capability that's pretty reliable and credible in the United States. It's looking at the question of how good are these generalized models going to get. Looking at the possibility of artificial general intelligence, even though that's something we struggle to describe, but their findings are pretty interesting. So the bottom line is they say, based on constraints of electricity, chip production capability, the ability to produce all the GPUs, the data to train up new models, and the latency limitations, they basically are telling us that the advances that were made in intelligence and capability of the models from the year 2000 to the year 2025 can happen again from 2025 to 2030. So that's like from 2020 to 2025, we went from GPT-2, which was a pretty hopeless model by today's standards already, to GPT-4, which is vastly superior. So that opens up an interesting question about where we might be by 2030, simply by doing more compute, putting more power and compute time into it with more GPUs and better GPUs, putting more data into it and improving the latency of the cloud compute. So without algorithmic breakthroughs, we may be looking at much more powerful models with high levels of intelligence and problem-solving capability. So yeah, if we look at where we went from GPT-2 to GPT-4, where we're now sort of at 20% on a key metric like Humanities Last Exam, it does give us an interesting question mark about where these models are headed to in the future. And as we heard from our earlier speakers, the bulk of these models are coming from offshore. United States and China are at the lead. Europe is playing a significant role. Canada has also invested very heavily in AI foundation model development. A small number come out of Australia, but we're not yet a really big player on the global stage in the creation of AI foundation models. The United Kingdom has had a look at this same question of AI foundation models in research, and a review was done by the UK Tony Blair Global Change Institute. Bottom line out of that report was they see this as not just something that's useful for science, but a deep restructuring of science institutes for AI. That basically they say that the significance of what's going on with AI and AI foundation models in particular is such that this isn't just making science faster, easier, quicker. This is a complete rethink about how we do science. So that's an interesting perspective that's out there. We've seen in the news today about legislation that's relevant. A key concern actually for anyone making an AI foundation model in Australia, I'm not sure about geospatial, but definitely large language models or models involving video and imagery, is copyright concerns at the current time would really limit what you could create in Australia, where those laws may not apply in other countries. So I think that's one thing. But late last year, the nation had got to the point of these 3 different pathways about creating AI legislation. The Productivity Commission has just released a report in Australia today cautioning too much legislation on AI, but there are quite strong views around AI being discussed across our parliament, with the possibility of an AI Act still with us as well, that would govern how we go about making and using AI foundation models. Last slide, we've just published this other report on Australia's artificial intelligence ecosystem, which really tried to say, what's Australia's strengths? Where are we specializing? Where is the activity happening in AI across Australia? I think the report probably creates a picture of an ecosystem that's mostly about using and applying AI models elsewhere, with a small but growing amount of foundation model development in Australia. We're more of an adopter economy when it comes to AI, more of a how do we apply it in this domain. But I think that there's lots of initiatives underway that might start to change that. The other thing in the report that I think is worth pulling out is Australia counted, during the 10 years up to 2024, we accounted for 2.3% of global AI research publishing. So we looked at all published, refereed scientific publishing on AI, and we found that Australia is 2.3%, which, given the size of our economy and our size of our R&D spend compared to the globe, we're punching above our weight there. But when it comes to product commercialization and creating AI models with commercial potential, we do pretty badly. So when you limit it to Australian inventors, only 0.18% of global AI patent inventions have an Australian inventor. They might be, we didn't count AI patents that are taken out in our jurisdiction, because that's often other companies that have developed an AI model elsewhere trying to protect it here. We looked for only ones with AI, with inventors of the AI patent from Australia, and that's a low share. So for some reason, Australia is not yet turning its AI knowledge into commercial products and systems. But I think if you look at Australia and start to ask the question, well, what's a portfolio of AI foundation models to support research, to support industry in Australia? And then we start building them, we might start to see that emerge sort of as the next wave of growth and development in Australia. So that's just sort of some high-level observations from me on AI foundation models. Thank you very much.
Fabulous. That's really great. Thank you very much, Stefan, Andrew, Ruzbek, and Guru, for that. I see that we've been getting the questions answered as quickly as they came in, but I actually do want to pick up, Guru, if you can pop your video on. I want to pick up on the question that Ella asked, and Guru's had an answer to it, about who should own Australian foundation models. And before I get the panel to add to what Guru said, which was that great question, but depends on who's involved in its development, and it does need to be open source. In the abstract for this webinar, we pose the question of, if we don't get involved, are we going to miss the boat, and all those countries that are spending the trillions are going to suck out the data that we have, because TERN data is all open source, etc. So, panel, who should own these foundation models? Should they belong to the private sector, or whoever spends the money on it, or do you think that they build on so many other people's efforts in getting the data and training it and stuff like that, that everyone deserves a share? What's your opinion? Who's going to start? And Andy.
Sure. I think in rephrasing the question, Beryl, you kind of answered it from my perspective, in that, a lot of these models are trained on information from people that have worked really hard and also open sourced it, put it out there. So TERN is a great example of this. So yeah, I think we're of the opinion that open source is very important. And, as Australia's national science agency, we would hope that it would be some sort of infrastructure that could be used by the Australian research community, but also other stakeholders in various sectors.
But also the fact that the data, that most of the data goes to these geospatial foundation models or foundation models in general are public data. And it's really good to have the model and the output also public for the public.
It's a long way to go. Stefan,
Look, I agree, and I think open source is great. However, for a start, we're likely to see private sector players in Australia putting forward LLMs and other forms of foundation model. They're in development. They're being cooked up. There are companies that are trying to be Australia's answer to OpenAI. Should it be one of the issues is copyright law here. If you do this in Japan, you're guaranteed to not have any issues with copyright law. You can just go ahead and build your LLM, commercialize it. And let's not forget that commercial market incentives to do this is an important aspect of the landscape to create these models. So yeah, there will be entrepreneurs who want to invest big bucks in the GPU, the compute, the expertise to create these. I think we want to, that's part of the Australian AI Foundation model making landscape. There'll be other sections which might come from more public sector where we want to make the models open access so that we can support the entire Australian research community and how to use those. And there might be that might be the case with geospatial. I think we want to be thinking a bit about national interest because all the other countries are like, how do we, if we do geospatial AIFM out of Australia, how do we make sure it benefits Australians and Australian businesses and gives us a leg up? We should be thinking through those questions. Do L8 what it used to be? It's a competitive and scary place. And the next 10 years of this globe, we've got to see how things pan out. But I think some of the scenarios is that the foundation models we currently use from overseas, maybe they aren't available under certain scenarios that we are currently used to. So that might be why we want to create our own. And let's also remember, we want to create our own AI industry. We do want open AIs out of Australia, and it could be in the space of geospatial foundation models. There's aspects that are open, but there's some really commercially valuable stuff that we want to develop and let that happen as well. So I think it'll be a mix of things. I think we need to think about our copyright laws and the legislation that's being discussed today in Australia. We need to think carefully about that legislation. There's been a change of mood in Europe. They brought out their AI Act last year, but at the Paris AI Summit this year, it was not on the agenda. It's about build capability and being competitive against America and China. That was everything out of France. And the French government has invested a lot in the company Mistral, which is a world-leading LLM. And there's, they now have that capability. And as we look to support the work of Australian governments with LLM, our concern is that all the LLMs we're wanting to use are made in other countries. So we got to trust them. We got to trust they're going to be turned on, they're going to be priced well, and that our data gets protected and they're not manipulating us to do stuff and they behave in an Australian way. Well, France and Canada have both made the investments, Cohere in Canada, Mistral in France, to be able to deal with that. So I'd say when you look at all the foundation models we're making, we're going to see a mix, public and private, and let's look at what the commercial and private sector can do alongside the open access too. Both will be important.
Thanks very much, Stefan. We've got a few questions coming in, and I'm going to direct this next one to Guru. Chris, I don't quite understand it. Guru, you're the head of our data. It says that there seems to be increasing interest in building foundation models from the edge, and TERN and other ground truth data seems likely to qualify it as edge data. Would it make sense for models to be built from the edge up? So please explain and please answer.
Probably, so whatever the data, even the TERN we have, I don't think we can build, there's enough data to train the model to cover the entire continental scale. So we may use the other data set as well. So there will be an additional data. So there is no way that, we can build a model with just the TERN data set. It can be, I don't have a right answer. Honestly, it can be like an edge up, as well as basically iteratively, build the model and then validate and then build the model kind of a thing. So we don't want to, train the model with a very small set of data set and then provide a, wrong information when it's output something.
Yeah.
So we should be very careful about that one in this case with the training with a small set of data sets.
And I've got one. I'm just not sure who's going to ask this one, but it's one that I always get when I'm out, and it's TERN. It's an environmental monitoring group. How can we condone the electricity use of an AI model? Isn't that hypocritical? Perhaps Stephanie, if you could very quickly comment on that from us.
Absolutely a fair call. Electricity use is going to be huge. These, it may be the main limiting factor to where we can go in terms of intelligence with these models. But let's make it renewable. Let's look at using renewable energy to take away the carbon emissions of AI model development. If you look into the future of any industry, anything in Australia, it just wants masses of more electricity. We've got a plan for that. And I think we can start to look at this sector to try and get renewable. But we also need new knowledge to solve where we're headed with climate change. Emissions are showing no sign of coming down. The concentration of carbon dioxide in the atmosphere from our weather monitoring station in northwest Tasmania, parts per million of carbon dioxide is just a straight upward line. I would suggest that, AI will create some emissions, but if it allows us to think of some solutions to this intractable problem, then it's probably worth doing on the pathway to where we go. So absolutely wouldn't want to dismiss it. It's a huge issue, and where we get all this electricity and water is going to be hard. We're going to have data centers springing up right across Australia. They're going to have a huge effect on our construction industry and the demand for electricity and water. Let's start to plan for it.
And Andy, I think you covered some of the next question about how AI models can be used to anticipate and avoid future risks to ecosystems, like people living in or near them. So very, very quickly, if you could just remind us. And
Sorry, what was the question?
how we can use the models to anticipate and avoid future risks to ecosystems and people living in or near them, really quickly.
I think that's a quite a difficult question to answer. But from my perspective, where I see value in these geospatial foundation models is being able to fill the gaps that we currently have in our observations. So I mentioned the cloud problem and being able to fill in those gaps. And if we can get more seamless satellite observations or generated from these models, then we could potentially produce better downstream products that could be used for downstream applications like assessing bushfire damage or flood mapping, etc.
Yeah, I can add a small reason for it. So one of the other ways that this model can use, for example, this new Google Foundation model is released annually. So you have the data from 2017 to 24. So you can do trend analysis, you can do monitoring. So this kind of model could help you a lot on getting more insight from the larger context, and monitoring is one of the ways that you can check how things are going and be able to anticipate what's going on in the future and if there is any upcoming risks. So that's another way.
That's good. We have got quite a few left in the box that we're not going to get to. So panelists, if you could stay online at the end, and we'll divvy them up and make sure everyone gets an answer to their questions. But thank you very much once again for stimulating such great questions, and thank you audience for giving us such good questions. And I'll just let you know that we haven't finished for the year yet. You still have the opportunity to get involved in 2 more of our webinars, atmospheric chemistry, and I'll have to get you at that, Andy, and then talk later in the year. So as we come up to the end of our time, do make sure that if you have any, moving on. If you have any questions for TERN, send them to our email box or check out what we're doing through our webpage. And with that, I'd just say thank you once again to everyone who's participated today. Stay online, panelists. We sort out those remaining questions. And we'll see you in 2 months. Thank you.
Thanks for the opportunity.
Thanks everyone for joining.